let's look at number 7. So for this polynomial, first we want to know where it is increasing and where it's decreasing. Now remember that your original function is increasing where the derivative is positive and decreasing where the derivative is negative. So I need to figure out where is my derivative positive and negative. So to do that, I'm going to make a sign graph for my first derivative. So I need to find the derivative and set it equal to 0 to find its roots for the sign graph. So first I'm going to go through and take the derivative. So the derivative of x is 1. The derivative of x squared is 2x. The derivative of negative x cubed would be negative 3x squared. So let's set that equal to 0. I don't like to factor when my leading coefficient is negative. So I'm going to factor a negative 1 out. That, of course, is going to change every one of my signs, so you can see my signs changed there. So now I have a quadratic to factor. So 3x squared breaks down to 3x times x, and then negative 1 would break down to 1 times 1 sign positive, 1 sign negative. So I've got it factored. Now let's set each of those factors equal to 0. So if I set 3x plus 1 equal to 0, subtract 1 from both sides and divide by 3. That gives me negative 1/3. Add 1 to both sides and I'll get x equals 1. So those are my critical numbers where my derivative is equal to 0. They are also the roots that go on my sign graph. So negative 1/3 and positive 1. All right, so now I'm going to pick a test point. I'm going to choose 0, and I'm trying to figure out if my first derivative is positive or negative. So I'm going to plug 0 back into the derivative. So if I plug 0 back into this derivative right here, I'm going to get 1 plus 0 minus 0, so I'm going to get a positive 1. So that means that right here at 0, it's positive. Cross a single root, the sign changes. Cross a single root, the sign changes. So there's my sign graph for the first derivative. So anywhere my first derivative is negative, my original function is decreasing. Where my first derivative is positive, the original function was increasing. And where my first derivative was negative, the original function was decreasing. So we're going to be decreasing from negative infinity to negative 1/3 and from positive 1 to infinity. And then we're going to be increasing from negative 1/3 to 1. Remember, for intervals of increasing and decreasing, you always use parentheses. You don't use brackets. All right, then the next thing they asked us was to tell where we had relative or local maximums and minimums. So you're going to have a maximum anywhere your graph changed from increasing to decreasing. That would also be then where the derivative changed from positive to negative. So you can see you're going to have a maximum at 1. You're going to have a minimum anywhere your function changed from decreasing to increasing. So that would be where your derivative changed from negative to positive. And so we're going to have a minimum at negative 1/3. So minimum at negative 1/3, maximum at 1. Now these are maximums and minimums on the original function. So to find the y value that goes with that x, I plug back into the original function. So you can see I'm going to take negative 1/3 and plug it back into this original up here. So that's what we did right here. And that gave us negative 5/27. So there's my relative minimum. And then for my relative maximum, I'm going to plug 1 back into that original function up there. And that would give me positive 1. So that would be my relative maximum. Then we wanted to know where is it concave upward and downward. Concavity is based on the second derivative, so we want to know where the second derivative is positive and negative now. All right, so here's my first derivative, so let's take the derivative of that to get the second derivative. Derivative of 1 is 0, derivative of 2x is 2, and derivative of negative 3x squared is negative 6x. So there's my second derivative. Let's set it equal to 0 and solve it. So if I do that, add 6x to both sides and divide by 6, I'll get x equals 1/3. So that is my possible point of inflection. That's my root of my second derivative. So I need to figure out where my second derivative is positive and negative now. So I'm going to pick a test point. So I'm going to pick 0. And since I'm trying to find where the second derivative is positive and negative, I plug that 0 into the second derivative. So if I plug in 0, I'm going to get 2 minus 6. So I'm going to get 2 minus 6 times 0. So I'm going to get 2 minus 0, or positive 2. So that means that at 0 it's positive. Cross a single root, the sign changes, and it changes to negative. So anywhere my second derivative is positive, my original function's concave up. Anywhere my second derivative is negative, my original function is concave down. So that means that I'm concave up from negative infinity to 1/3, and I'm concave down from 1/3 to infinity. So there are my intervals for concavity. Then they asked us to tell where we had a point of inflection. And remember that you have a point of inflection anywhere you change from concave up to concave down, or from concave down to concave up. That's also where your second derivative changes signs from positive to negative, or negative to positive. So for us, we have a point of inflection at 1/3. Since it is a point of inflection of the original function, you are going to take that 1/3 and plug it back into the original equation. So when I plug 1/3 back into the original equation, I get 13 over 27. Now, again, as I mentioned to you earlier, the thing that is so time consuming is when you have to plug x back in and find y. So on your quiz tomorrow, there will not be erroneous y values. So what I mean by that is that if you plug 1 in and get 1, there won't be a point sitting there that's 1, 1, and then another point sitting there that's 1, 3. So if you know that x is the correct value, you can assume that that y value is the correct one that goes with it. So I have plugged in all of your x's and found your y's for you, just to make it a little more expedient for you. All right, so then just a little bit of review. Remember that anywhere your derivative is negative, your original function is decreasing. And where your derivative is positive, your original function is increasing. Anywhere your derivative changes from negative to positive, you have a relative minimum, and anywhere your derivative changes from positive to negative, you have a relative maximum. Anywhere your second derivative is positive or your first derivative is increasing, your function will be concave upward. And anywhere your first derivative is decreasing or your second derivative is negative, your graph will be concave downward. Where it changes concavity, you have a point of inflection.